Hello, everybody. All right, so welcome to our online classroom. So this is grade 11 university level physics, SPH3U. We're going to do a lesson today that's not really course material, but this is sort of something that we're going to need everywhere. It's part of the course material. Don't get me wrong here. It's just we're in unit 0 still. We still haven't started the actual stuff. We're going to talk about something today which is a little bit abstract, and it might cause you some consternations along the way. It might be a bit confusing, but it's okay. We're going to be using this skill of significant digits throughout the course. All right, this is not something that you need to master right away. We're going to keep using this skill throughout the course all the time, and eventually it'll become second nature. Right away, though, it's going to be a little bit strange, and that's okay. Just take your time. The more and more we practice, we have 9 weeks now. We're going to practice this, and we're gonna master this. Okay, but if it's a bit confusing at the beginning, don't worry about it. All right. Basically, what we're going to talk about today is a rounding rule. When we had math, right, we learned these rounding rules where we had examples where it says, round to the nearest hundredth, tenth, or something like that, or round to 2 decimal places. And we continually do this in our trigonometry or whatever. They round to 3 decimal places or something. What we're going to develop today is a sort of rules that allow us to know when to round without being told. Right? Depending on how much information is given to us in the initial question, we're going to be able to know exactly how many decimal places to round to. And this is by recognizing how many significant digits there are available to us, how much information, how much precision there is in the initial data that they tell us that they think of. Now, for us to do this, we got to think about sort of the nature of physics, right? This is a physics class, but what is physics? It's a difficult question to answer, sorry. But we can think of physics as what we call a empirical science. What do I mean by that? Physics as an empirical science. Now, what that means is that whenever we do anything in terms of a theoretical understanding of physics, or when I say physics, I mean understanding the physical world, the rules that govern our physical world around us. We can really think of physics as being a sort of a deep underlying set of rules that explain pretty much everything. There's a very famous quote by a guy called Rutherford. He was a physicist. Actually worked in Montreal, in the University of Montreal. He was the one, you may have heard of him from grade 9 science, maybe grade 10 science, the Rutherford model, discovering the hard positive nucleus in the atom, this tiny little, with the gold foil experiment. Maybe this rings a few bells. He was also pretty much not a very nice guy. He was a bit of a curmudgeon, and one of his famous quotes is that everything is physics, the rest is stamp collecting. Okay, what he means by that is that physical laws explain everything. They explain chemistry. They explain biology then, because biology ends up being, a lot of chemistry, and then biology explains psychology, and you can go down this forever, right? And then but the underlying bedrock of everything are strict physical rules, and that's the study of physics. That's what we're going to be studying in this class. But if we're going to make up these rules, if we're going to make up a set of rules, some physical laws that have to govern the universe, it's very easy to know if we're right or wrong. We just have to do measurements. We have to do experiments. And if our physical theory is contradicted by some measurements, some experiments you do, your physical theory is wrong. Right? It's very easy to say, this is the rules that govern the universe. But then you have to actually prove it. You have to actually show some empirical evidence. That's this word empirical. Empirical means that there's some physical evidence, some experimental evidence that shows that you're right. Okay, so there has to be a correspondence between your theoretical understanding and your experimental proof, your measurements that are taken. Okay? So, for example, something like string theory. In the 80s and 90s, the big physics idea was something called string theory, this frightening idea that everything's made up of strings that are vibrating and whatever. And it's sort of fallen out of fashion now because inherent in the theory is that there's no experimental proof, which sort of discounts it from being a real theory at all. So, um, in the end, we have to, at some point, you can come up with whatever theory you want, but at some point you have to show that it exists in the real world with some empirical evidence. Okay? So let's think about what we mean by measurements. Okay? So what do I mean by a measurement? I'm going to take a ruler, let's say, and I'm going to measure something. And I measure it's 6.2 centimeters, right? Do I know that it's exactly 6.2 centimeters? Right? What's the sort of fuzziness around that value? Could it be closer? Could it be like 6.15? Could it be 6.24? Something like that. There's got to be some sort of some error bars, some sort of space that 6.2 is somewhere here, but there's this sort of fuzzy region that it exists in. I can then get something like a very fine vernier calipers, those things, the little calipers that pinch on something, and I can measure it. Now it's 6.23 centimeters, or probably more than that, or something like a very precision tool that can now have higher precision that can get us a more accurate number that tells us what the new measurement is. Okay, so the tools that we use will actually define how well we know what the number is. And our measurements themselves, it doesn't matter how precise your tool is, there will always be some uncertainty. All right, so let's go back to the ruler. So 6.2. Do I know what that second decimal is? Do I have any idea of what the 6.2 something? Like, what could that number be? We have no idea. It's a sort of a fuzzy cloud there that we don't know about. Okay, and we have to take that into consideration when we're doing calculations. Let's say I'm gonna calculate something with that distance, 6.2. I'm gonna multiply that distance times a force calculation or something. But I have a very fine, precise electronic tool that measures the force. So I have a very precise, many decimal value for the force. But if I multiply that highly precise number by that very low precision number, my answer cannot have more precision than the lowest precision that we have. Okay, so even if I have a whole bunch of data and one of the values is very precise, the precision of my answer is limited by the least precise one. Okay, and there's going to be rules that we're going to have to follow that allow us to keep this uncertainty and precision around. So all measurements have an inherent uncertainty defined by the tool we use to measure it. So for a ruler, we say that something like 13.2 centimeters, it's plus or minus 0.1 centimeter. So it could be somewhere between 13.1 centimeters and 13.3. Right? We have this sort of 0.1 centimeter, this 1 millimeter fuzziness around our value, our precision. Right? This number, 0.1 centimeters, we call the precision of our measurement. Okay? So we're going to have to come up with some rules to deal with these uncertainties, because that uncertainty is going to limit our final answer, the precision in our final answer. Okay? So we're going to use something called significant digits, and we're going to have to be able to look at a number and let's go through here. Look at a number and be able to figure out how many digits actually matter. Okay, so this is a lot here, but we're just going to go. There's a lot of rules here. I'm going to go through them pretty quickly, and it's because it's easier to learn about significant digits by actually doing the problems. But I'm just going to go through these quick notes. This will all be available on the Weebly. If you'd like, it's probably a good idea for the notes. When you're taking the notes, when you're watching these videos, write them down in a notebook. Make your own notes. Add your own things. Like I might talk about stuff. You can add your own information that you think is relevant. You can take out stuff you think isn't relevant. You can write down examples. I'm going to scribble on these with a little electronic pen. You can add my little annotations. It's probably a good idea, even though you're going to have everything available to you digitally, it's probably a good idea to still have a notebook. Okay, so let's go through significant digits. The following digits are significant. Any non-zero digit is going to be significant. Any zeros that are between non-zeros are significant. So for example, 102.05, those zeros matter. Those zeros are not placeholders. The choice for zero. So zeros are the sort of crux of this idea. Zero can either be information, like 102. That zero cannot be anything else. Right? It can't that number cannot be 192. That's not the same thing as 102. So that digit is holding measurement data. Okay, some zeros will not hold measurement data. So anything after a non-zero, so let's say 405, so 405,000. That 5 is significant. That 5 matters, right? That 5 can't be anything else. But those zeros after that, that's where the fuzzy region begins. So those zeros there just tell us how large the number is. It tells us that we're in the hundreds of thousands. We're in 4. In the 4, that digit, that largest digit, is in the hundreds of thousands. So it tells us how large the number is. So those zeros here, so this 0 in the middle, that matters, right? Because that can't be anything else. That can't be a 1. That can't be a 6. Right? That one matters. But these zeros at the end, these are placeholders. And what I mean by placeholders is that they tell us how big the number is. Okay, they tell us where, like if I wanted to write this in scientific notation, actually scientific notation is awesome because it allows us to not have to worry, because I can write this as 405 times 10 to the, how many? Let's see. The decimals here, so I go 1, 2, 3, 4, 5. So this is going to be 10 to the 5. Okay? So this now, I know that this has 3 significant digits. Oh no, I misread it. Wow. Okay, so sometimes they'll write 405000 and there's going to be a decimal at the end. That's a silly way of writing it. I don't like that, but whatever. That means that these digits matter, okay, because of that 0. Zeros at the end of a number are, these are not placeholders. I am wrong. Sorry, I didn't see that 0 there. So that has 6 significant figures because of that 0. So I would have to write this. If I wanted to write it in scientific notation, I'd have to put all those zeros behind it. Right? So then we have 1, 2, 3, 4, 5, 6 significant digits. If that decimal wasn't there, I'm never going to write a number like this with a decimal on the end. I'll just write it in scientific notation, so there's no ambiguity. There's no confusion by that. That's ugly. I don't like that. So all zeros to the right of a decimal point and at the right of a non-zero are also significant. So anytime I have a decimal, so this decimal right here, everything afterwards matters, even that 0 at the end. And these zeros after the decimal, because that decimal is there, these zeros matter. So both of those numbers have 4 significant digits. Again, as I go through the note here, it's going to be confusing. Just bear with me, and when we get to the examples, it'll make a lot more sense. The following digits are not significant. Any zeros before, so all these zeros, these don't matter, because this tells us just how far over I have to write. Because I could write this as 4.03 times 10 to the 1, 2, 3, 4, 4, negative 4. Right? That's equivalent to that. And that also, this tells us right away that there's 3 significant figures. Using scientific notation will actually help you a lot because there's no ambiguity. There's no confusion. In this case, these zeros in front, they just tell us how small the number is. Right? We're in the, what's that? That's 10 thousandths. So, right? That'd be tens. No, wait a sec. I'm wrong. Tens, hundreds, thousands, 10 thousandths. No, I was right. Okay, so it's 4 in the 10 thousandths. Okay, and we know that because we can write it as is this. And it has 3 significant digits. There's 3 digits of measurement data, of certainty, we could say even. Right? Now, if there's ever a constant, if there's ever some physical constant, like gravity or Planck's constant or something, some number that I give you in the formula sheet, in our there's a reference section that has a whole bunch of physical constants. Any of those numbers, we're going to assume that those scientists who gave us those numbers have better, more accurate devices to measure things than we do. And we're going to assume that they have enough significant significant digits to be more significant than our data. And we're always going to treat them like they have an infinite number of significant digits. We're not going to worry about them. So for example, in this formula here, the G here, that's not going to consider in our, we're not going to worry about that in our calculations and worrying about how many significant digits our answer has. Our question will always have less. Also, the 2 in the formula, that's not 2 as a measurement. That's 2 as a sense of doubling something. Multiplying it by 2 doubles the number, right? And that's a mathematical operation. That's what we call a Platonic number. It exists not as a measurement of 2 centimeters, 2 goats, 2 whatevers, 2 cats per donut. It's just a mathematical concept of doubling something. So that has an infinite number of significant digits. So we call that an exact number. All right. So in this case, the only thing we would worry about is this displacement here would have an uncertainty because we measured that. The 2 is an exact number. It's 2.0, and then the zeros go on forever. And G is 9.81 meters per second, and we're going to assume that's perfect. Okay? Just because those scientists who gave us the number have better devices to measure stuff than we do. Now, how do we actually do operations with these? There's going to be 2 rules. There's an addition and subtraction rule, and there's a multiplication rule. For addition and subtraction, we always round to the lowest number of decimals. So the decimals matter in addition and subtraction. The lowest number of them in the measurements that are provided. So example here, I have 2.6 plus 12.57 plus 0.395. So this has 3, this has 2, and this has 1. When I add them, I plug in my calculator, it gives me the number 15.565. Now, I can't say that that's my answer because my first number is 2.6. I don't know if it's 2.61, if it's 2.57. I don't have enough measurement data in that first number. That's my limiting measurement. So I have to round it to 1 decimal place. So I round it at the 5. And I'll see that the 6 is greater than 5, so I round the 5 up to a 6. So my final answer will be 15.6. So when we do calculations, you're going to plug in your numbers, you're going to do your calculations, you're going to write your answer with the decimals, and then you're going to do one extra step. You're going to round it to the correct number of significant digits, or decimals in this case. All right, so the addition rule, again, lowest number of decimals. Multiplication rule now, very similar, but it's the lowest number of significant digits. All right, so we have to round to the lowest number of significant digits. So what's 6 times 6? Let's go back to grade 4. I think that's one of the very first things that you memorize, because we know that 6 times 6 is 36, right? And that is correct mathematically. 6 times 6 is 36. However, in physics, in a physics lab, if I have a measurement of 6, that only has 1 significant digit. So 6 times 6 is 40, because I have to round 36 to 1 significant digit. And you might be looking at this like, what? That doesn't make any sense. 6 times 6 is not 40, and you're correct. 6 times 6 is not 40. 6 times 6 is 36. But in a lab, in an experiment, if I do 6 times 6, I have no numerical data after the first significant digit. So I cannot say it's 36. That 6 could actually be, the first one could actually be, if I used a more precise measurement, it would be 5.7 or something. And then the other one could be 6.4, and that would be goodness knows what, right? So when I have 6, both of these numbers will round to 6, right? So when I say 6 times 6, it's a fuzzy number. There's not very much data, so I can only say it's equal to 40, which is kind of gross. I am aware. That's weird. So that's the first weird lesson of the day. 6 times 6 is 40. And it's not actually 40. 6 times 6 is 36. Okay, but in terms of the number of significant digits, I can't say it's 36. I don't have enough information to say it's exactly 36. I only have enough information to say it's around 40. Okay, so it's an idea about how much evidence we have in our answer. All right, that's weird. All right, again, scientific notation is a very convenient way of keeping track of significant digits. It makes things easier. Also because in physics, we have some very, very large objects like the Earth, and some very, very small objects like atoms. And we have to be able to deal with them without writing millions of zeros all over the place, right? So radius of an atom, for example, hydrogen atom is 0.00000000000000053 meters. Now writing that in your notes would be cumbersome, to say the least. So instead, we write it as, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's going to be 5.3 times 10 to the negative 11 meters, right? Or 53 angstroms. Sorry, 0.53 angstroms. Angstrom is this is just a quick little aside here. An angstrom, which is an A with a circle on top, 1 angstrom is 10 to the negative 10 meters. It's one of these funny units that we use in physics. I think it's Swedish, I'm guessing, with that circle on the top. But anyways, radius of the Earth, 6,380,000 meters, or 6.38 times 10 to the 6 meters. All right. And here also, we have no ambiguity. We know that this has 2 significant digits. We know that this has 3 significant digits. Makes things quite easy. All right. So let's do a few examples. I'm gonna do the first question for these. All these practice sheets. There's 2 practice sheets that are available on the homepage of our Weebly. Here, let's quickly just jump over there. Right here. So this is the front page. If you go straight away to this URL, it'll bring you right to here. And if you scroll down, there's the significant digits note. That will be the note that's the PowerPoint that I'm showing you guys. This video, once I've recorded this, I'll upload it to YouTube, and I'll put the link right here. And these are SD, so significant digits worksheet number 1, significant digits worksheet number 2. So these are available to practice. And the second page is the solutions, actually. So if you get stuck, flip over. Don't cheat, but do the whole thing and then flip over and check your work. Okay, so all the solutions are there. So let's do a couple. 246.32. All these digits matter. So it's 5 significant digits. Okay, 1.008. These zeros are between non-zeros, so they matter. So this has 1, 2, 3, 4 significant digits. This one here, these zeros only tell us that it's in the hundreds of thousands. So this number only has 1 significant digit. There's 1 actual piece of measurement data. The rest of them, these are all placeholders. Okay, they don't matter. But let's say this one here, 305.670. This 0 on the end looks like a placeholder here, but it's after a decimal. So that one does matter. So this has 6 significant digits. Same thing with 1.0000. This is telling us that we know precisely that all of these numbers after the decimal are 0. Okay, as opposed to the 700,000, where this is just telling us how big the number is. We don't know what these numbers are. It could be 712,342. Right? But we don't know exactly what those numbers are. We just say that they're zeros because that's how big the number is. But we've shown that these four numbers, these four zeros after the decimal are there to show us that it has, 5. Apologies. This has 4 zeros, but there's 5 significant digits. Okay, how about this one here? 0.00340. So which of these zeros actually matter? The first non-zero digit is the 3, which tells us that these numbers here are just placeholders, but this 0 is after a decimal and after a non-zero, so this 0 does matter. So this has 3 significant digits. All right, 107.854, that has 6, 4, 3, 5. Ooh, this is a good one. 0.001. These digits, these zeros in here, there's no non-zeros and no non-zero digits in front of them, but there's a decimal, right? So this one, these zeros, they only tell us how small the number is. So this only has 1 significant digit. And this last one here has 6. All right. So hopefully that helps. This is again, I don't want to scare you guys by saying 6 times 6 is 40 in physics. It's a very strange idea. We're gonna keep practicing this. This is a skill we're just gonna need throughout this course. Whenever we do labs, whenever we do any calculation, the last step is always going to be looking back to the numbers we have, which one is the lowest number of significant digits, and rounding to that number of significant digits. So this is something we're just going to continually do all the time. If you are confused, don't worry about it. It's okay. We're just going to keep practicing. If you try the practice worksheet, check the answers. If you're still stuck, please feel free to contact me. You can get a hold of me through Teams. You can get a hold of me through email. So find a way to get a hold of me. Typically, just send me a chat message through Teams. That was your homework to do. That was your first homework, was actually to send me a chat message. So you all should be able to get a hold of me. Go to that chat thread and send me a message. You can try to call me through Teams. I can try to get a hold of you through Teams as well, and we can figure this out. But again, don't be too worried about this. This is just something that we're going to be doing throughout the year. Eventually, on tests and, for example, or assignments, if you're not rounding to the right number of significant digits, you will lose some marks. Okay, this is an important skill. At the beginning of the course, the few first things, I won't care. I'll just circle the answers and say significant digits. I won't take any marks off, but eventually I will start taking off marks. So it's an important skill to learn. All right. So what I'd like you to do again for homework, just do those worksheets, and if you get stuck, just ask for help. All right. So first lesson done. Good job. All right. So try those problems. Get a hold of me if you're stuck. And I'll be talking to you later. All right. Take care. Stay safe.